Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. You've heard me mention my upcoming AI Summit previously, and while I am just so excited because it's right around the corner. The event takes place April 30th and May 1st in Las Vegas in conjunction with the Interop ITX conference. If you're an IT, technology, or business leader who needs to get smart on the broad spectrum of machine learning and AI opportunities in the enterprise, or someone in your organization fits that description and could benefit from a level up in this area, you should definitely make plans to join us in Vegas. I'll be presenting an introductory session on ML and AI fundamentals, and we'll have deep dive sessions on AI for NLP and conversational applications, computer vision, and Internet of Things on Monday. And then on Tuesday, we'll be discussing data collection and annotation, operationalizing and managing AI, and building out your AI strategy. Then you'll have a chance to discuss your organization's unique AI opportunities and challenges with our distinguished experts. To learn more about the event, head over to twimlai.com/AI Summit for details, and be sure to use code Charrington for 20% off of your registration. Okay, in this episode, I'm joined by Christopher Lum, Research Assistant Professor in the University of Washington's Department of Aeronautics and Astronautics. Chris also co-heads the university's Autonomous Flight Systems Lab, where he and his students are working on the guidance, navigation, and control of unmanned systems. In our conversation, we discuss some of the technical and regulatory challenges of building and deploying unmanned autonomous systems. We also talk about some interesting work he's doing on evolutionary path planning systems, as well as a precision agriculture use case. Finally, Chris shares some great starting places for those looking to begin a journey into autonomous systems research. All right, let's roll. All right, everyone, I am on the line with Chris Lum. Chris is a research assistant professor at the University of Washington in the Department of Aeronautics and Astronautics. And Chris has joined us today to talk about some of his work in autonomous vehicles. Chris, welcome to the podcast.
Hi, well, thank you so much for having me, Sam.
Thank you for joining us. I'm really looking forward to diving into the discussion here. Why don't we get started by having you tell us a little bit about your background and how you got involved in autonomous vehicles?
Sure. Actually, my background's fairly simple. Basically, I've been at the University of Washington for around, what is this now? About the past 18 years. I started in 1999 as an undergrad, and I finished my PhD there in 2009 in Aeronautics and Astronautics. And I've been in my current position as a research assistant professor for about the past 2 years or so. I think I've heard it referred to as being a lifer, and I can't really tell if that's a term of endearment or maybe it's some sort of a cautionary term of what happens if you get stuck at the same institution for too long and can't get a real job. But in any event, I've been interested in unmanned systems and aircraft probably since around the late 90s, early 2000s. So the University of Washington was actually part of the team that put the first robotic aircraft across the Atlantic Ocean around this time frame, and pretty much ever since then, I've been fascinated with applications of unmanned aerial systems.
Oh, fantastic! I've noted this in previous podcasts on this topic, but and you've got I'm sure, a unique perspective on this, being so close to Boeing, but currently we think of autonomous vehicles largely in the context of self-driving cars, but there's a ton of work that has happened in this space around flying vehicles.
Yeah, absolutely. And I know several of your recent guests have all been talking about self-driving cars. And as you mentioned, that's pretty much a very hot topic of research right now. But I'm not entirely versed on the history of self-driving cars, but I would probably guess that autonomous aircraft and some of the research in that realm has been going on quite a bit longer than that. It started to gain a lot of traction kind of in the early 90s here. Some of the technology finally came to fruition to kind of enable a lot of the current iteration of what you might think of as an unmanned aerial system. But yeah, this research has been going on for quite a while in this space. And in some senses, I think it's an easier problem, and in some senses, it's definitely a more difficult one.
I'm really looking forward to hearing you dig into those two areas. But for context, why don't we get started? Or for context, why don't you tell us a little bit about your research focus?
Sure. So the lab that I direct up at the University of Washington is called the Autonomous Flight Systems Laboratory, and basically we're interested in pretty much researching any technology that's related to guidance, navigation, and control of unmanned systems or automation in general here. So a lot of the times that has projects like looking at autonomous mapping here, or maybe performing risk assessment of an unmanned mission, or looking at maybe path planning. So there's a couple of different projects we've looked at in the past, but the one flavor that unifies them all is they have some technology that's related to an aircraft or autonomy in general.
You say autonomy in general, meaning other types of vehicles beyond aircraft?
Yeah, absolutely. We've looked at some things like some obviously ground robots, some surface vehicles like autonomous boats here, but in general, a lot of the times we've historically been interested in the algorithms that are running on these systems here. And a lot of the times the autonomy aspect or the algorithm that you're running, it doesn't have to be flying on an aircraft. You're trying to do some path planning through a complicated environment, or you're trying to build a map of an environment, and you could do that using an aircraft, or if it's more pertinent, you could do that with a ground vehicle or a surface vehicle. So our major focus in the past has really been developing the algorithms that would drive these vehicles or enable some sort of functionality. And the fact that it flies is almost more of a historical trend with our group. Is we've just been more comfortable with the aircraft and have a little bit more experience with the aircraft. But as I'm sure you're well aware of, and many of your other guests have talked about, autonomy spreads out and is much larger than a particular vehicle that you happen to be using.
You mentioned boats, and I mentioned, or we mentioned Boeing. Boeing, I think earlier this year, purchased a company that was doing like unmanned underwater vehicles for sea exploration. Did you ever come across that acquisition, or are you familiar with that company?
I am not familiar with that particular company or application that you mentioned, but there are faculty here at the UW that have looked at underwater vehicles. In fact, that's a major research focus here at UW. There's a vehicle called a sea glider, and it's an underwater vehicle, and basically it operates by changing its buoyancy. So sometimes if you're trying to dive, it is a little bit heavier than water, and then it has an internal bladder which can change its buoyancy to be a little bit lighter than water. So it's got wings on the outside of it, and you can imagine as this thing is descending through the water column, it can effectively glide as it's descending. And as it comes back up, you basically just change the buoyancy to be a little bit lighter than water, and now it just glides in the opposite direction. So now you're gaining altitude or getting closer to the surface, but you're basically able to affect forward motion with this. So there's been a couple of groups at the University of Washington that have been very interested in the underwater robotic side of things, using things like the Sea Glider or custom-made hardware as well.
Okay. So what are some of the major challenges in the areas that you're focused on? Things you mentioned, path planning and some others.
Well, I guess that's really an interesting question, because in this space, there's a lot of, as you mentioned, different challenges. And right now, I would almost bin these into two different buckets. There's obviously some of these technical challenges that people are interested in right now, like doing detect and avoid, right, where an aircraft would be able to find another aircraft and deconflict and avoid a collision. There's technical challenges like that, but one of the almost bigger problems or obstacles, well, maybe obstacle is the wrong word. Maybe we should just keep using the word challenge, but is one of a regulatory one. The regulatory environment in the U.S. right now is not the most conducive to conducting cutting edge research with unmanned aircraft, but it's definitely getting better here. So if you want to talk about challenges, interestingly, probably more of the issues that we deal with right now trying to conduct research with unmanned aircraft is almost we spend more time trying to deal with some of the regulatory issues than we do with the technical challenges right now.
And what's your approach to that? Are you taking a research-oriented approach to that, or is it more of a, traditional kind of advocacy, lobbying, whatever the right terminology is there?
Yeah, we kind of do a little bit of both here. Obviously being a research group here, we do try to push a lot of these technical projects forward here from a pure basic research standpoint. But as you mentioned, the lobbying and the advocacy and the public perception is almost just as important. UAS right now seem to be this very polarizing topic right now. A lot of people love them. People like you and I, and probably the majority of the audience of people that listen to this podcast are, very technologically savvy. They see the potential benefits here of unmanned aircraft and unmanned aerial systems, and really think that it's probably one of the next major revolutions in the aerospace industry. So you got that side of the fence, but then on the other side of the fence, you have a large chunk of the public right now that don't think that they're a good tool and perceive UAS as something that the government is going to use to invade your privacy here. So you have this polarizing space where you got some people love it, some people hate it. So I think one of the jobs here, obviously the people that are working in this space, is probably to try to change the perception of some of the people that are a little bit negative or on the fence on these systems, and show them that there really are a lot of positive applications for this type of technology right now. So advocacy is a large part of the work right now, I think, in order to try to change that perception.
I'd like to get to some of the details of the research specifically on the technology side, but just for sake of completeness, when you think of the positive benefits, or more specifically, the positive use cases or applications, what are the things that you tell people to try to win them over?
Yeah, the great question. For maybe a little bit of historical background, as you probably know, UAS have their pretty much an established history kind of coming from a military perspective. So a lot of the times you hear about stories of the military using these to conduct intelligence, surveillance, and reconnaissance, or other types of operations. But nowadays, the commercial and the civilian applications of these are really opening up here. So, for example, one of the technical applications that I think has a lot of promise here in the U.S. in the next several years here is this concept of precision agriculture. So the idea here is, can you use unmanned aerial systems to augment or help effectively agriculture and farming here? So, for example, one of the projects we're working on right now is, you can maybe call it just an aerial mapping project here. That's kind of the large umbrella term that it falls under. It's a very popular one. Maybe I'll preface that. It seems like right now everybody and their dog wants to use an aircraft to try to provide some type of aerial map. So, we kind of wanted to jump on that bandwagon a little bit as well. And we've done a couple of projects where, we would like to use a aircraft or some kind of imaging system to gather large data sets here over a farm here. And the data that you gather is very interesting. You could do something simple like using a normal electro-optical camera to get your, red, green, blue channels of what does a farm look like from the visual, optical range of sensors, and provide that information to a farmer. That's maybe the first layer here is, you would have to take all of these images and stitch them together here to generate a high resolution orthomosaic of some kind of area. And then, maybe taking that one step further, there are other applications where you can put on different types of sensors, like a multispectral imager that might be able to get you some of maybe the red edge or the near IR bands of radiation on that same area. And what you can actually do with that is people have been looking at things like a normalized difference vegetation index or an NDVI image. What this is it's basically a plant health map. So what it will do is not just show you what does the farm look like from the air, but it can show you in this other, another perspective of that same farm. You can kind of get an idea of which plants are vigorous or healthy, and maybe which areas of the farm could use a little bit more attention. So that's obviously has a lot of potential applications to helping agronomists and farmers learn a little bit more about their crops and their products.
So when I think about that application area, there are, and try to decompose it into different problems that one might apply machine learning and AI to, there's certainly you talked a little bit about the sensors, and, there may be some ML in like stitching together, creating these ortho mosaics and doing it in I know I forget the term. It's like, essentially rectification, like correcting for Earth curvature and other anomalies, maybe removing cloud cover or things like that. Across the different things, aside from the sensor load and the various things related to, the sensor data. And I guess the other big one is obviously the processing of the data and applying it to the use case. Like, what do these images tell us about the health of the underlying agricultural system? It strikes me that in some ways, like the autonomous flight aspect of this, might be one of the easiest problems, right? At least if you separate out the collision avoidance thing. Like, even consumer drones, you could kind of lay out like a waypoint, a GPS waypoint grid, and just have the UAS follow that waypoint grid. And I guess this is really all a setup for, like, what are all of the things that, someone like me who's distant from this doesn't even think about, that make it way more, nuanced and complex than one might think.
No, you bring up a lot of really good points there, Sam. And in fact, I kind of wanted to dig in a little bit more on that last statement you made, where the flight planning and the actual execution of, say, an autonomous flight. You're right. That is kind of the boring part. That's kind of a solved problem at this point. It's a fairly mature technology. Just automating an aircraft to do some kind of a mission. Right now, we've got undergraduates in our lab right now. They go out and they buy a $200 little avionics platform, which is this open source hardware and software package, and you can integrate that onto a pretty much vanilla radio controlled aircraft, and you have yourself a quote unquote drone right now that you can tell it where you want it to fly, you can tell it how high, you can tell it when to land. All of that is great here, right? And autonomy.
I'm sorry for interrupting. You happen to know the name of that package? I'm sure folks might want to check it out.
Oh yeah, absolutely. I mean, there's a bunch of different ones you can find right now, but I think probably the most popular package, at least for the introductory level of getting into UAS here, it's a system called a Pixhawk. Okay. And it's basically an Arduino-based system here, where you would load on the open source firmware packages called it's the Ardu Pilot family of software. And that can do things from flying a plane or flying a multi-rotor or doing a ground robot. So it's really a lot of fun. It's sort of the Arduino package for doing unmanned systems. You're building your own unmanned vehicle. It's a pretty easy way to get introduced to these systems. But, like we were talking about earlier, that's sort of the easy part of this, right? That's the solved portion of the problem here. So nowadays, unmanned aircraft and UAS, they're really a means to an end, right? All you're trying to do in a lot of the research topics now is carry some sort of sensor, right? All you need here is that unmanned aircraft to take sensor somewhere that you want and take the data that you want. and then doing something with that data or extracting the relevant information. That's where a lot of the research is right now. And that's maybe where some of the, the machine learning and the AI that, I'm sure you're very familiar with comes into play here for doing things like you're mentioning the stitching of the photos together here. So in that sense, I don't think we're necessarily a cutting edge developer of AI. We more use a couple of packages that will do the structure from motion and the photogrammetry and matching all the key points up together and stitching it together. That's something that you can almost purchase off the shelf right now. But extracting the information, like you mentioned, and doing something with that information and having some kind of policy that you can act upon based on what you perceive, that's where it's a little bit more interesting right now. And I think that's probably a little bit more where some of the strategic level research is going on right now.
Okay. And is that how, with a research group focused on unmanned aerial systems, does your group get involved in kind of that level of the discussion, or is it primarily the, kind of the infrastructure for autonomy?
Can you expand a little bit on that? What do you mean?
I think I know the answer to this based on the example that you gave, but getting down to the application of, say in precision agriculture, like is your research and your group's research interests going down to the application itself and some of those areas, or is it more on the platform and the autonomous flight? Some of this, given that that there's a base level of capability that's well established and commoditized, there are also, I imagine, kind of there's a frontier there somewhere that might be, object avoidance, or it might be, maybe it's, incorporating variability. Like, how do you update your mapping grid with if it's very windy or something like that? And, or I saw on your website, you talk about like swarming behaviors and things like that. Do you tend to focus at that, these kind of infrastructural or platform kinds of things, or, is your group in particular also kind of, focusing on these application level questions?
Yeah, I think I see what you're saying, and my answer might not be the most satisfying here. Our group, I don't want to say tends to be scattered here, but we do have multiple different projects looking at kind of different aspects of autonomy in general here. And I will preface all of this by a lot of it is driven by the student initiative here. So if some students have a project that they're very interested in, we do as much as we possibly can to support that and enable that type of research. So that might be one of the reasons why we do look at a kind of a wider spectrum, almost a breadth first search rather than a depth first search in some of these topics here. So we are very interested in some of the applications here. So going back to that precision agriculture discussion that we talked about, I think you put it exactly right when you said that some of these components are commoditized and readily available. So a lot of the workflow that we mentioned earlier about planning a flight plan, generating or obtaining all these pictures, stitching them together, that is also fairly mature. You can buy a lot of packages to do that. Now the question would be, what do you do with that information when you have it back? So that's where I think some of the frontier that you mentioned is happening right now. So it's one thing to be able to tell a farmer, here's what your farm looks like from a NDVI or from a health perspective. What do you now do with that information? So one of the things that we've looked at in the past is what's been done historically. Well, what do farmers do if they have a problem on their farm? Well, they'll go hire, say, a crop duster, right? And I'm sure you've seen crop dusting aircraft before. There are these biplanes or right. low-wing aircraft which have 500 gallons of effectively toxic chemicals, right? And then they would go carpet bomb the entire farm to make sure they got an even application of this everywhere, right?
Mhm.
So that's one way to approach the problem, right? But if you had more information, like say you were able to send out a surveying drone or multiple surveying drones to get this information about where on your farm actually needs this, well, then you might be able to do a more surgical application of some of this pesticides, herbicides, what have you. So we've actually in the past we've developed a automatic crop dusting aircraft here. So it's a small, about 6 foot wingspan aircraft which has about a liter of aerosolized payload. So some students were looking at, would you be able to use this in conjunction with some of this data that you get from the mapping side of things to now touch up areas of your farm instead of using a carpet bomb, policy? Could you use one or more of these aircraft to deploy and just hit the areas that you need to in your farm? So that's maybe one of the application levels, but we also look at some of the regulatory and more the larger platform issues because, as we just talked about there, it's you have to build some platform. You usually have to do some hardware to enable some of these ideas that you want to do. So that's one thing I think that makes our group a little bit unique here is that we do have a lot of people that are very interested in spending time getting their hands dirty, building some specialized hardware, conducting flight tests, things like that, rather than just doing the simulation in the lab and making sure that it works. We actually want to go out and fly it.
The precision crop dusting application sounds really difficult. Like I'm wondering, can you share the specific results of the research? Like when I think about the issues that go into that, in particular, on the chemical delivery side, you've got this targeted aerosol that you're trying to deliver. It sounds, I'm imagining that you'd have to fly pretty low in order to deliver it, and then you have all the turbulence and air effects off of your vehicle that's going to scatter your aerosol. Like how does that even work, or how well did it work?
You again have a real knack for asking the exact questions that I think need to be asked here. So there are a lot of challenges associated with it. So one of them that you mentioned right away here is the fact that you need to be fairly low to have an effective dispersal of these systems here. So some of the students did have to look into some technologies like automatic terrain avoidance here. So you need to be able to maintain a very specific altitude above the ground level. We didn't get a chance to actually test that too extensively. We went out and the farm we flew this at, luckily, was fairly completely flat, and they actually had just mowed all the grass the day before. So it was it worked, but again, I don't think we stressed the system very much there. The other thing that was very difficult with this project, and it maybe segues into some of the other research we've done here, is if you think about it, when you have this farm where certain spots on your farm might have the need for application of the pesticide or the payload and others don't, you basically wind up with the large traveling salesman problem, right? You've got this spatial grid here, but then you have only certain locations you need to visit, and then you only have one vehicle with a certain amount of payload that has certain constraints. So effectively, it turns into a traveling salesman problem. And then if you want to scale this up, we were talking about the vehicle only has about a liter of payload. Well, I don't think a farmer wants to be out there all day, shooting 1 liter of payload, having it land, refill it, exactly, going back out again. So maybe scaling this up to a swarm of vehicles where you could have multiple of these aircraft going out and doing this might cut down on the amount of time necessary to do this. But now, instead of a one-dimensional traveling salesman person, you have like N agents that you want to do traveling salesman with effectively. And that can be kind of challenging. So some other projects in the past that our groups looked at have been maybe trying to tackle some of these problems using evolutionary computation and algorithms. I believe you had a guest in the past from UT Austin talking a little bit about this, maybe from the financial side of things. But
right. That was Risto Mikalainen.
Okay, right. I remember hearing one of them. That was a really good podcast, and I kept trying to think about what were some of the parallels to maybe some of the evolutionary algorithms that we would apply here for unmanned aircraft. And this is one of the places where it would work here. You mentioned you have multiple aircraft or multiple agents, and then you have environmental problems. I think earlier we were talking a little bit about what if you have wind, what if you have turbulence. If your environment is complicated, it gets a little bit interesting. So one approach that I think has has yielded some reasonable results here is trying to do the path and the task planning using evolutionary computation rather than, say, traditional optimization techniques.
Okay. You mentioned swarms of vehicles. This is also something that's been researched, at least theoretically. I think we're a lot closer to application now with these small, inexpensive vehicles than previously. But I think some of this stuff goes back to the 70s, even maybe. Or what kind of things have you looked at, or what have the research results been of your different forays into this? Like for the precision agriculture, like how far did you get with that, and how did you formulate the problems?
Well, I definitely don't want to claim to be an expert in this arena by any means, but I mean, I'm happy to talk about some of the things that we've done in the past. Maybe going back to that evolutionary computation example, that was a project which had multiple vehicles involved in it, and maybe you could call it a swarm. I guess the terminology swarm seems to have different contexts and different meanings depending on who you're talking about here, but from our perspective, maybe we would think about this as just multiple vehicles trying to achieve some kind of common goal. So in the past, we've done things like searching with multiple vehicles. So we have a cooperative group of vehicles or in your team, and you need to spread out and search a potentially spatially complex environment here, which might have obstacles, which might have danger zones, or might have regions that you don't want to be in. So we looked at trying to apply multiple vehicles in these scenarios here rather than just a single vehicle. And searching with multiple vehicles is by no means a new topic. As you mentioned, this has probably been from the 70s or earlier. I think a lot of the early work with, I believe Alberto Elfs did a lot of work in occupancy grids and occupancy-based maps back in the 80s here. And we sort of tried to extend some of that work here to using multiple aircraft to search an area cooperatively. So that might be one aspect where you might consider this to be a swarm application, although in that sense, the vehicles, they were not actually tightly coupled together. They were more cooperatively interacting with one another. So that was one application, I guess, where you have multiple vehicles. We've done other projects here where you try to have a more rigidly structured swarm. So we did some work with Boeing a little while ago where we wanted to have a dynamically reconfigurable formation. So the idea would be you have a formation of vehicles, either in a line or a diamond or some kind of configuration here. And for the most part, that's usually fine and dandy. You can go flying around in the atmosphere with this formation and maintain its structure, no problem. But you've got people now talking about trying to do urban navigation, like in cities, and you can imagine now you've got constraints, you've got obstacles. So this swarm needs to be able to reconfigure itself and adapt to moving around these obstacles, or maybe going through choke points, like trying to get through a window or a narrow intersection. So we looked at some of that work there with multiple vehicles and swarms here.
When you're looking at these multi-vehicle problems, whether it's this formation flying problem or formation missions or the group search, what are some of the approaches or algorithms that come into play?
Yeah, that's a good one, because right now it seems like a lot of the research is focused on sort of decentralized algorithms which are able to scale well. So the idea there would be you try to communicate with your nearest neighbors, or using some type of graph topology to determine communication and how these vehicles interact. And I think one of the reasons that's gained a lot of traction here is because it's somewhat scalable here, right? If you have a somewhat decentralized algorithm where you don't need information from everybody else in your team, you only need information from certain vehicles, that tends to be a little bit more scalable than, say, a centralized or some all-to-all communication topology where the communications costs and the scaling costs just exponentially increase with the number of vehicles. So if you want to do a large number of these, a decentralized approach might have a lot of interesting advantages here. That being said, some of the things that we've looked at, particularly in the past here, has actually been a little bit more heuristic or a little bit more rules-based. I think it's really great to be able to talk about scaling this to 50, 100, 200 vehicles, but in reality, the state of the technology is at such a level here that I think you'd be lucky if you can get 5 vehicles cooperating together simultaneously. So right now, we've personally been focusing a little bit more on the rule-based or the heuristics or the centralized type of algorithm to coordinate multiple vehicles. So that search work that we talked about earlier, it was basically you have this star topology where everybody communicates with a centralized coordinator. Not every single agent needs to talk to every other agent, but every agent needs to be connected to a centralized coordinator to allow each vehicle to compute what it thinks is the optimal path for it to take next.
But that is the calculation of the optimal path to take next is done by the vehicle itself as opposed to the coordinator centrally determining that and just giving the vehicle a flight path.
Correct. So the vehicles would be able to make their own decisions here, although it does rely on information or inputs from the centralized coordinator.
Okay.
And the coordinator role can change. It doesn't necessarily need to be a ground station. It could be one of the vehicles. But as long as you have a central agent or some kind of clearinghouse that would have some information that all the other vehicles need, that's what we were using to make some of these systems like the searching or the evolutionary path planning work.
And is that central coordinator or the central information, is that just state, or is there also, are there any elements that need to be centrally computed?
I guess it would depend on the application. So for example, like the searching application where we had this environment and you wanted to send out a swarm of vehicles to find some kind of target, like a lost hiker or a boat, something like that. The information that the coordinator maintained would be a map or the state of the world. So you're right. In some sense, it would have some state here that the vehicles could then have access to make their own independent decisions on what to do next here. In the case of the evolutionary path planning here, the idea with that was, you would have multiple vehicles trying to achieve some type of team-based goal here. And to do that, each vehicle needed to compute its own flight path to achieve something. And what the centralized coordinator did would be able to look at every vehicle, effectively made a bid on a task here. They would say, based on my tactics, based on my capabilities, based on my constraints, in order for me to execute a certain task, I think it's going to cost me X amount of whatever the metric is, fuel, time, money. And then the coordinator would then be able to effectively act as like an
auction,
an open market, like a free market. Right. The coordinator would be able to pick and assign tasks to the vehicle that could do that for not necessarily the cheapest individually, but the cheapest for the entire team, right? So the coordinator would be able to assess and evaluate who needs to do what so that the overall team could achieve the mission.
It strikes me that in that case, you run into potential like local optima type problems, or the cost is potentially highly dependent on like the time horizon and the sequence of tasks that each of the vehicles takes on. Did you look into that aspect of it?
Yes, you're absolutely right. And I think, again, I by no means want to claim to be an expert or even well-versed in this, but evolutionary algorithms and any kind of optimization in some of this very complicated problems here are always probably subject to some type of local minima here that in for a complicated system can be very difficult to assess. Is this a local minima? Is this a global minima? How are we doing relative to what else options are out there? So you definitely could fall into that trap. One thing that made this system unique here is, you mentioned this idea of given the amount of time that you have to compute or whatever your horizon was, one feature that we really wanted to bake into this evolutionary path planning system that was developed here was the concept of feasibility here over optimality. So you can probably imagine if you have aircraft flying around, it's great if you were able to have some sort of what you would call a optimal flight path. That's great. But if it takes you 3 hours to compute an optimal flight path, that might not be so great if you have actual aircraft in the air, right?
Right.
It's kind of like having the space shuttle and you want to reboot the computer here and have everyone hold their breath, right? You probably don't want to do that. So instead, feasibility is almost more important than optimality, right? Each of these vehicles need to be able to have a feasible flight path and at least something they can do and execute at any given moment. So what we wanted to do was make sure that the evolutionary algorithm only sort of considered feasible trajectories or solutions at any given point. So you might think of this as some type of interior point method from a larger optimization standpoint, but that I think was something that made that a little bit interesting and unique here because optimality wasn't as highly prized as feasibility. And I guess, if you think about it long enough, optimality is, by definition, it's subjective, right? It's whatever cost function or utility function you decided to cook up and decide to apply to the scenario. Who's to say there isn't a better optimality function or cost function somewhere else? So in a lot of these cases, your constraints actually are more important than what you have decided as this utility function to apply.
Oh, that's a really interesting way of thinking about it, and something that probably gets lost in a lot of the conversations about optimizations. Did you look at though the feasibility cost, I guess, for lack of a better term? Like, did you compare that to the optimal for a given cost function and try to get a sense for, what was the cost of operating under fixed resource or time constraints?
Gosh, you've got me in a corner there here. I don't recall the specific details here, but I'm going to have to punt a little bit on that and say I don't believe we actually did an in-depth sensitivity study on that front.
Okay, great. So for folks that are interested in learning more about this type of research, are there any particular, you've mentioned a couple of different projects that you've worked on. Are there specific papers that they can go and track down to learn more about the way you approach that problem?
Yeah, absolutely. We have a couple of papers on our lab website here. Again, most of them are compartmentalized by these different projects that we're working on. So yeah, please or let me know. I'm happy to share projects or papers with anyone that's interested.
Yeah, we'll definitely include links to the ones that we talked about. Hopefully you can help us pull together a list of those, as well as the website as a whole. For folks that want to learn more about the field in general, do you have any starting places that you tend to point people to?
That's a really good question here. So
I guess it's hard to define the field, right? There's so much.
Right. That's exactly what I'm trying to think about right now. Is like we've had a really good discussion here about, there's the technical field for sure, things like the detect and avoid, or the path planning, or the information processing on the data you return from these aircraft. That's definitely one exciting area of the field. But the ones that we're seeing a lot come out right now are. There's a lot of interesting flight test and practical application, and people actually going out and conducting experiments and gathering data with this. It's almost a branch of I guess, the more mature sort of field robotics area, right? Is the aircraft, I think, in the U.S. are now starting to be able to catch up to some of the field robotics that people have been conducting with ground robots and elsewhere for a long time. So there's a lot of exciting details about that. So there's a couple of companies that we've worked with in the past that are actually conducting a lot of flight tests. It's people at the University of Washington, over at UC Boulder, UT, or at Texas A&M. There's a lot of different groups that are doing this type of work. So it's hard for me to point to one exact, I guess, paper that would be helpful. So yeah, I apologize. I probably don't have a specific reference to look at.
Yeah, maybe let me ask like this: if you were talking to someone who was early in their research career and they asked you, what are some specific kind of interesting problems that would be a good place to start to dig into, how would you advise them?
Yeah, that's another good one. I guess at this point, where things are really interesting, at least from our perspective here, is we're doing a little bit of work right now. We're seeing a lot of interest in this idea of risk assessment of UAS. So if you're not sure on exactly what part of UAS you're interested in, risk assessment is actually an interesting way to take a look at this, because what's happening right now is a lot of people, in order to gain waivers or the ability to conduct their operations with under FAA jurisdiction, need to provide some type of risk assessment showing that their operation is safe. And by doing that, by conducting this risk assessment, you're forced to sort of take a overall look at not just a specific technology on board an aircraft, but the entire flight operation envelope and operation in general. So you actually have to look at the end-to-end mission using a UAS. So that's, your checklist, that's your area of operations. Then the technical aspects would be that's your platform and what kind of avionics you're running, what kind of control algorithms. So if you're able to understand the risk associated with the given UAS, that's a really good way to try to get a bird's eye view of what are some of the challenges and issues associated with UAS and the research that's going on with them right now.
So we talked earlier about a software platform like ArduPilot. For a system like ArduPilot, how would you go about conducting a risk assessment on that part of it? Does that involve like detailed code path reviews? And are you trying to get to how do you even characterize the risk associated with that part of a system?
Yeah, that's an excellent question here. And I think there might even be some parallels and some ways we can look at self-driving cars here as well. The risk assessment, there's multiple ways you can look at this. One is exactly like you mentioned here. You can look at a detailed low-level implementation of trying to characterize each component here associated with an aircraft, look at mean time between failures, try to calculate or estimate or some otherwise get a handle on the reliability of a given component, right? Mm-hmm. And you do that for one component, then you do it for another component, you do it for another component, and you can kind of see this also becomes, while it's very detailed, it's difficult to do this and scale this because I don't know if you just go into Google Images, right, and you type drone or unmanned aerial system and you look at the images page, drones come in all sorts of different size, shapes, taxonomies, avionics. There's just so many different ways that you can configure an unmanned system that is really not standardized, and trying to do that for any given system pretty much becomes fairly intractable quickly. So the other way you can sort of look at assessing risk of a given UAS operation or a mission is at a more macro level here. You can look at things like, how often do I expect this to collide with another vehicle here? And try to do a larger level risk analysis. I mean, in fact, this is really interesting. We published a lot of technical papers here looking at, things like path planning here or mapping or GPS denied navigation or things like that. But our most popular publication is actually looking at a model to assess the risk of a given UAS mission on a large level, like what we were talking about just now. Because if you think about this, UAS are a very interesting new paradigm in terms of aviation safety. So historically, right, there's three parties or three entities you have to care about if you're flying an aircraft, right? You have to make sure that the people on board your own aircraft are safe. B, you have to make sure people on board other aircraft are safe. And then C, you have to make sure that people on the ground, like these bystanders or pedestrians, that they're safe. Right. And this is kind of very similar to a self-driving car, right? A self-driving car, it's the same thing. You got to make sure that the person in the car is safe, people in other cars are safe, and pedestrians are safe.
Right.
Now, the unmanned aircraft, though, brings a interesting twist on this topic here, right? Because historically, if you just make sure that your own people on board your own aircraft are safe, the other two categories follow directly, right? If my aircraft is safe, I probably won't hit other aircraft, and I probably won't hit people on the ground here. So the implication of that is your aircraft needs to be extremely reliable and robust and safe, right? The airframe itself needs to be reliable, because if you ensure that, you ensure the other two parties are safe as well. And that's the exact same for a self-driving car, right? So I've heard many of your guests previously talk about safety is important for self-driving cars. That really means, again, making sure that the vehicle itself, the self-driving car, is safe and therefore won't endanger anyone else. Now, with the aircraft, though, if you take out the person on board the first group, right? If you take off the people on board the aircraft, now you just have to worry about those other two categories. That's people in other aircraft and people on the ground. What that kind of does to you here is it means you can actually sort of have a semi-unreliable aircraft, as long as you make sure that it doesn't hit other aircraft and it doesn't hit other pedestrians on the ground here, right? So that's why I think you've seen a lot of these unmanned aircraft nowadays. They're nowhere near the level of reliability of a manned aircraft, right? Mean time between failures are fairly often. Actually, you have these LiPo-powered, these battery-powered, effectively souped-up hobby aircraft going out and doing these types of missions here. And as long as you conduct them in, like a remote enough area where you're not endangering those other two categories, you can probably conduct these type of operations in a perfectly safe manner here and still have the same level of reliability and safety as a manned operation. It brings a slight paradigm shift to the idea of where these systems can be used.
Which brings us full circle back to one of your opening points, that regulation in particular and the overall perception of trustworthiness of these systems is just as important as the technical bits and pieces in making it all happen.
Right. Yes. Regulatory compliance and making sure that the operation is safe, I think, is a huge portion of the research and the public perception associated with the UAS right now.
Well, Chris, this has been a fascinating discussion. I appreciate you taking the time to share with us. Where can folks learn more about what you're up to?
Oh, absolutely. We've got a website, and actually, I'm almost kind of embarrassed to admit this here, but in this age of social media here, we've got a lot of very savvy students here in our lab who have set up a nice Facebook page as well for our group here. So we've got those sort of environments on the internet that people are absolutely welcome to check out. And if anyone is near the University of Washington or in the Seattle area, I would invite them to swing by the lab, talk with us. We also have a flight testing facility near here where we fly every once in a while, and we try to invite people that are interested to kind of come out and observe and maybe fly with us. So there's we would love to have any interaction with anybody in the area or elsewise.
Great. Well, I'll include a link to your page on the UW site and get with you about any other links that it would make sense to share.
Oh, thank you. That would be great.
Awesome. Well, thanks so much. I appreciate it.
No, thank you so much for having us. It's been a real honor to be here.
Thanks, Chris.
All right, everyone, that's our show for today. For more information on Christopher or any of the topics covered in this episode, you'll find the show notes at twimlai.com/talk/129. If you're not an ML or AI practitioner, but you want or need to increase your depth in these critical areas, remember to check out my upcoming AI Summit at twimlai.com/AI Summit. Thanks so much for listening, and catch you next time.